This story begins 130 years ago. By the 1870s, scientists were able to demonstrate that matter was made of very small spherical particles they called atoms. They had measured the mass and size of most of them and knew a lot about the way they behaved. The chemists and the kinetic energy physicists had accomplished a lot, but did not know what was inside the atom. Atoms are smaller than a wavelength of light and can only now be seen using an electron microscope. It took a series of experiments to discover what atoms are made of. In the late 1800s, physicists were experimenting with electricity. Hans Geisler and his colleagues found that if they passed electricity through a tube with most of the air removed, a faint glow was produced within the remaining gas. Later, William Crook noticed that with a better vacuum, a green glow appeared on the inside of the glass. This could be made quite bright if the glass was coated with phosphor. Crook showed that the glow was caused by rays that traveled across the vacuum from the negative electrode, or cathode, to the anode. The actual rays are invisible, but we have shown them here with green shading. These rays cast shadows, which proved they traveled in straight lines. They were deflected by a magnetic field. It was already known that a moving negative charge behaved this way. But were the rays particles, or were they light? To find out, a wheel was inserted between the electrodes. The wheel was constructed with spokes like small paddles and placed in the path of the beam. The paddle tips were coated with phosphorescent paint. So the rays had momentum. Therefore, they must have mass and velocity. The experiments showed that cathode rays are a stream of negatively charged particles that have mass. The electron had been identified. In 1897, a British scientist named Sir Joseph John Thomson modified a Crookes tube so that he could produce a fine beam of cathode rays or electrons. He found that they were always the same, no matter what metal the electrodes were made of. The tube design let him accurately measure how the cathode rays were deflected by magnetic and electric fields. An electric field caused the cathode rays to deflect in one direction. A magnetic field caused them to deflect in another. This method of deflecting an electron beam is still used in television picture tubes and computer monitors. At the back of the tube is an electron gun. Surrounding the neck of the tube are the coils of an electromagnet that deflect the electron beam to the exact place needed to produce a picture. A color television tube has 3 different phosphors in the screen, each emitting a different color when struck by electrons. The beam is directed accurately enough to produce the right colors. By measuring the strength of the electric field needed to balance the deflection of cathode rays caused by the magnetic field, Thomson found the ratio of the charge on an electron to its mass. But he couldn't measure only one, only the ratio. If E could be measured independently, then the mass of the electron could be found. Between 1909 and 1916, Robert Millikan carried out experiments to measure this charge. Millikan's apparatus was simple. Two parallel metal plates with a uniform potential of 5,000 volts between them. Fine droplets of oil in a mist were allowed to fall between two charged plates. The droplets pass through X-rays and lose electrons, becoming charged. They pass through the hole in the top plate. The top plate was made positive, so that the negatively charged drops were forced upwards. Each negatively charged droplet had just two forces acting on it: the gravitational force pulling it down, and the electrical force pulling it up. When he balanced these two forces by changing the voltage, a droplet became suspended. He knew the mass of the droplet, so he could calculate the size of the forces. Then he calculated the charge on the drop. He found that the charges were always multiples of an extremely small number. There were none in between. The smallest steps represented the size of the charge of a single electron. Because Thomson had found the ratio of charge to mass, Millikan could calculate the mass of the electron. The charge was indeed tiny. Electrons are all the same, each with the same charge and the same mass. In 1886, Eugene Goldstein noticed tiny bursts of phosphorescence behind the cathode in a discharge tube. He discovered rays flowing in the opposite direction to cathode rays. These rays were called canal rays because they were produced by using a cathode with holes or canals in it. They traveled away from the cathode in the opposite direction to the cathode rays. But what exactly were they? They were not coming from the anode, they had the wrong properties. They seemed to come from the low-pressure gas between the electrodes. Perhaps the cathode rays, or fast-traveling electrons, collided with the atoms of gas in the tube. They could be knocking electrons off the atoms, leaving them positively charged. If this guess was correct, then positive ions were being attracted to the negative cathode and appeared to be rays. Goldstein and others performed deflection experiments to find out their properties. By balancing the deflection caused by magnetic and electric fields, they found the charge to be positive and the same as the electron, or multiples of it. They also found that they were much heavier than electrons. They were positive ions. This beam of positive ions is used in an instrument called the mass spectrometer. Once produced as a beam, the positive ions, or cations, are deflected by passing them through a magnetic field. The lighter they are, and the higher their charge, the more they are deflected. Thus, a mixture of different ions can be separated from each other and identified. This is how the mass spectrometer works. Isotopes of an element, which have slightly different masses, can be separated from a beam of their ions by the magnetic field. This is how the relative atomic mass scale of the elements has been measured. J.J. Thomson, in 1906, used a modification of his cathode ray tube to send electrons into hydrogen gas. He discovered canal rays with the smallest mass. His high-speed electrons had knocked electrons off the hydrogen particles, leaving each particle as a positively charged ion, a bare nucleus. Later, Rutherford suggested calling these smallest positive ions protons. Although they were shown to have the same charge as the electron, their mass proved to be some 1,860 times greater. The proton had been identified.